Now, before we get started on the lesson today, are there any questions over the homework? Questions over the homework assignments? We good with the homework assignments? I will pass out the, actually, why don't I go on and do that now? That is the wrong hour. The missing assignment sheet will not have the bonus because I went on and filled them in as zeros. And that doesn't hurt or help you. It's 0 out of 0. So if you do want to do those that is still available. You can do those. The note sheets for them are over there. There are two. One of them, GB 4.6, is the one we did before Thanksgiving. 4.6, just 4.6 is the one we're finishing today. Get them done before the end of the year.
So, if I have tournament Friday?
Friday's fine. Next Tuesday's fine. Also, if you're looking for the homework problem sets, Amy, and needing to find those, they are on Google Classroom. Didn't mean to get you there. All right. We're going to do one more of these here, writing the polynomial function of least degree with the given zeros. Yeah. As much as I want to do that other one, we're going to do this one here. So, whenever we do these here, polynomial of least degree, we set each one of the zeros equal to x. We're setting x equal to each one of our solutions. Now with our complex or rational terms, if we're given 1, so here they told us one of the solutions was 1 plus I squared of 5, it means we also have its conjugate, 1 minus I squared of 5. So we have these here. Questions on this so far? Now looking at this one here, we can actually already tell what the degree of the solution is going to be, because our biggest exponent, the degree, tells us the number of solutions. And here we have how many solutions? 3, which means the biggest exponent for this here has to be 3. It's kind of a giveaway telling us this here. So if we end up with something, or you work some of these here and get a degree bigger than the number of solutions we have, we know we did something a little wrong somewhere in the process. Now, first step is to get each of these equal to 0. So we're moving it over. So the first one we would subtract 3, telling us x minus 3 is equal to 0. The next one we would subtract 1, telling us x minus 1 is equal to I square root of 5. And then subtract our I squared of 5 from both sides, giving us x minus 1 minus I square root of 5 is equal to 0. Questions on either one of these first ones here? We good with these first two? Yes? Well, the only difference between this x minus 1 minus I squared of 5 and the last one is that it went from positive I squared of 5 to negative, which means it's going to be essentially the same thing when we get done, except instead of having minus, we're going to have plus. Now we can do this one step at a time because we could subtract 1 first, telling us we have x minus 1 equals negative I squared root of 5. But then to get it equal to 0, we would add I squared root of 5, giving us this here. And once we get them equal to 0, we're going to multiply them together. Now, if we actually had 4, we could do these 2 at a time. And what I mean by that is, let me get a different color. Because if I said I had x plus 3 in the front, I could just multiply the x plus 3 and x minus 3 and do our x minus 1 minus I squared root of 5 times x minus 1 plus I squared root of 5. We can do more than one multiplication at once. But since we only have one of them in front, wrong direction. We're just going to do these here first, because whenever we have complex conjugates, we're going to multiply them first. It's going to make things a little bit easier. And it'll give us a lot less terms to work with when we have to finally simplify everything down. Our first step is going to distribute the x. Our x times x would be x squared. X times negative 1, negative x. X times I squared root of 5 is plus xi square root of 5. Then we can move on to our negative 1. Negative 1 times x, negative x. Negative 1 times negative 1 is going to be plus 1. And negative 1 times I squared root of 5 is negative I square root of 5. And lastly, we're going to distribute our negative I squared root of 5. Negative I squared root of 5 times x is negative xi square root of 5. Our negative I squared root of 5 times negative 1, negative times a negative, is a positive I squared root of 5. And lastly, our negative I squared root of 5 times I squared root of 5, well, we can do that by hand, or luckily, the graphing calculator will do this for us. I squared root of 5 times negative I square root of 5. Now we can do this in the calculator mainly because our square root of 5 times square root of 5 is 5, and our I squared will simplify out to positive 5. So what that's telling us is the last term is plus 5. Questions on this so far? Now we have 9 terms there. We're going to simplify that down. Well, our xi squared root of 5 and negative xi squared root of 5 become 0. Our negative I squared root of 5 and our positive I squared root of 5 become 0. And after doing this here, all of our radicals and I terms are gone. And what that leaves us with is x squared. Our negative x minus x is negative 2x. And our positive 1 and positive 5 give us plus 6. Last thing we need to do is distribute these two here, and then we solve, or not solve, but simplify. X times x squared is x cubed. X times negative 2x is negative 2x squared. And our x times 6 is plus 6x. We'll also distribute the negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x is plus 6x. And negative 3 times positive 6 is negative 18. Questions on this here? Questions on anything we've done so far? Last thing we need to do is combine like terms. X cubed is the only x cubed term. Our negative 2x and negative 3x combined to be negative 5x squared. 6x plus 6x is plus 12x. And then we have our minus 18. Questions on this here? But that's it. That's all we have to do for these here. Any questions on any of this here? We ready for the last theorem of this chapter? Descartes' rule of signs. If we have a polynomial function with real coefficients, so the number in front of them are real numbers, we don't have any imaginary numbers, I terms, then the number of positive solutions, number of positive real zeros, is equal to the number of sign changes of the coefficients of f of x, or is less than it by an even number. Okay, so we're just going to look at that first. So if we want to find the number of positive zeros, we take the function, this here, and count the number of sign changes. So if we look at x to the 6th, to x to the 5th, does the sign change? Yes, because x to the 6th is positive, x to the 5th is negative, so that's one sign change. Now we go from x to the 5th to x to the 4th. Does the sign change? Because x to the 5th is negative, x to the 4th term is positive, so does the sign change from here to here? Yes. Now we're going from the x to the 4th term to x to the 3rd. X to the 4th is positive, x to the 3rd is negative. Does the sign change? Yes. X third, x squared is negative to negative, so no. X squared to our x term, negative to negative, so no. And lastly, our x term to constant, no. So the number of sign changes we have is 3. So the most positive solutions we could have for this polynomial equation is 3. We can have 3 solutions. Now it did say or less than it by an even amount. What's the smallest even number? So we can keep subtracting 2 from it until we hit a negative to give us all the other options. Well, 3 minus 2 is 1 minus 2 is negative 1. We can't have a negative number of solutions. So this is it. So what it tells us is the solutions that we're looking for this here, we can either have 3 positives or 1. So if I graph it and find 2 positive solutions, it means that there's a third one out there somewhere. Maybe out, because again, our graph only goes from negative 10 to 10 on the x. Most likely it means the other positive solution is bigger than 10, and we just need to find it. But if I only find 0 positive solutions, that means there has to be at least 1 there. I'm just not seeing it yet. So this is helpful because, well, it gives us an idea of what solutions we should look for, as well as which ones we can eliminate from our rational zeros. It gives us an idea to narrow the scope of the possible solutions. Because going into any problem, this quadratic, or not quadratic, this higher degree polynomial function at the start, before we do anything, well, the solutions could be anywhere on the number line. It could be any real or complex number. But with the rational zeros theorems and Descartes' rule of signs, it helps eliminate some of those choices. Questions on this so far? So we found our number of options for positive real zeros. Okay, let's look back at the theorem. The number of negative real zeros is equal to the number of sign changes of the coefficients of f of negative x, or less than it by an even amount. F of negative x. Well, for positive, we were looking at f of x. We didn't have to do a thing to it. For our negative zeros, we're looking at f of negative x, which means every x in the function has to be replaced with negative x. So we'd have negative x to the 6. minus 2 times negative x to the 5th, plus 3 times negative x to the 4th, minus 10 times negative x to the 3rd, minus 6 times negative x squared, minus 8 times negative x, minus 8. Questions on this here? Give you a second to write that, because y'all might need a second to write that. We good with this here so far? Still writing? All right. This next bit, I'm going to go on a little anecdote so that we can, it's going to lead into this. But what we need to do next is simplify all these negative x to a power. Yes? Now, you don't have to write this, but I would at least just follow along with this here, because this does have a point. Negative x to the first would just be negative x, yes? Well, negative x squared would be negative x times negative x. Negative times a negative is a positive. X times x is x squared, yes? We did negative x cubed. Well, we're just taking what we had previously and multiplying it by what? Negative x, yes? Well, our x squared times negative x is really what we're saying. X times x, not x times x, x squared times x would be x to the 3rd. But a positive times a negative is a negative, yes? Yeah. Negative x to the 4th. Make sure I write this correctly, because the 4th power would be outside. Well, we're just taking the previous one, our negative x to the 3rd, and multiplying it again by another negative x, yes? X to the 3rd times x is x to the 4th. But a negative times a negative is a positive, yes? What would we expect negative x to the 5th be? It would be negative x to the 5th, yes? Because all the ones that have an odd power, that negative stays. All the ones that have an even power, that negative becomes a positive. And it works out that this is true every single time. That if we have an odd power, it's still going to be negative. But if we have an even power, that negative is going to turn into a positive, yes? And the reason that this is helpful is because if I look through this here, and we can look at x to the 6th first. The 6th power is even, yes? So that means that negative is going to turn into a positive, leaving me with just x to the 6th power. And that's fine. The next one after it is negative x to the 5th. So we know that negative sign is still going to be there after we apply the 5th power to our negative x, yes? But that negative is going to affect the number in front of it, yes? So the way I think of it is if that power is odd, we still have that negative, it's going to change the sign of the constant term, or our coefficient. Since it's already negative, that negative 2 times a negative is going to make it positive 2. And as we saw kind of in those examples, the power with x stayed the same. It's still x to the 5th. Because really what we're saying that we have is negative 2 times negative x to the 5th. Negative 2 times negative x makes it positive 2. If we look at the next one, R3, well, the negative x to the 4th power is even, so that negative is going to come into a positive. Positive 3 times positive x to the 4th is just plus 3x to the 4th. Negative 10 times negative x to the 3rd. We still have x to the 3rd. But that negative, because it's an odd power, is going to stick with it. So we have our negative 10 times our negative. The negative and negative make a positive, so it's plus 10x to the third. Next one we have is negative 6 times negative x squared. Well, we will have x squared, but the negative with it is now positive because it's an even root. Even power, not root, power. Which means our negative 6 in front of it stays negative 6. Negative 8, well, we can still do the same thing here because with our negative x, it's to the first, even though we don't write it. First power is odd, so that negative will stay, and negative 8 times negative x becomes plus 8x. You ready for the last one? Yes? Minus 8. Because there is no variable attached to it, so it doesn't change. It's just still the constant term. Questions on how we did this here? Because, I mean, we could go through the whole process of multiplying negative x to the 6, negative x by itself 6 times, and seeing what happens to the sign. And we could do this with all of them, but really it's going to hold true that anything to the even power, anything to an even power, 2, 4, 6, 8, 10, 12, whatever the sign of the term in front of it is, it will stay there. Because our x to the 6, let me get a highlighter, was positive. It stayed positive. Our 3x to the 4th was positive. Before we applied the negative x, it's still positive. With our x squared term, it was negative. It stayed negative. And well, then we have our negative 8 because it's not even or positive. It's not even or odd. It's not odd or even. So it's just negative 8. Negative 2x to the 5th was negative. It is now positive. Our x cubed term was negative. It is now positive. X term was negative. It is now positive. If the power is odd, the sign in front of it's going to change. If the power is even, it stays the same. And that's it for simplifying this negative x to the power. Now, all we need this for is figuring out the number of negative solutions. So our number of negatives. We'll do the same thing. From x to the 6th to x to the 5th, it goes from positive to positive, so there is no sign change. X to the 5th, or x to the 5th term, x to the 4th, no, positive to positive. X to the 4th, x to the 3rd, positive to positive, no. X to the 3rd to x squared, yes, we went from positive to negative. X squared to x, negative positive, yes. Our x to constant, 8 to negative 8, yes. So the most negative solutions we can have is 3 or less than it by an even amount. So we can keep subtracting 2 from it, just like we did with positives, and say we could have 3 or 1. Questions on this here before we write out our answer? We're ready to write the answer out. Because our answer for this here is we need to know every possible combination of these here. Every possible combinations of positive and negative solutions. Now, normally, when I do these here, the way I first start off is this here. It's going to be a chart. Now, the way that we do Descartes' rule of signs will always be in this chart form. And I have a feeling most of y'all can take a guess at what P and N stand for. Positive and negative. Does anybody have a guess what C is? Not constant, but we can have either positive solutions, negative solutions, or our complex, our I terms, our non-real solutions. And it doesn't state it in the theorem, but the best way I can say the complex zeros for this theorem are the missing ones, or the ones that are missing. So, whenever I set this up, I always look at the most. I don't ever do the -2 when I find the number of positive and negatives. because we said the most positives was 3, and the most negatives that we could have is 3. I always look at however many we can have. For the most, I don't ever really start doing the subtraction to once we find the positive and negative solutions. So we have this here. Questions on this so far? Now, we do still have the complex, yes? And I stated a minute ago that it's the number that are missing. So what's the degree of this here? What's the degree? It's 6, yes? How many solutions should we have? 6, because the degree tells us the number of solutions. So if we had 3 positive solutions and 3 negative solutions, how many solutions do we have? How many are we missing? So the number of complex would be 0. That's why I say it's the number that's missing. Questions on this here? This next part is nice and can sometimes be confusing at times, because now we need to figure out the arrangements of 3 and 1 with positive and negative, yes? I don't try to go through and make sure I line them all up. What I do is I start with the negatives and keep subtracting 2 from it till I can't anymore. So the first thing we can do is 3 minus 2, which is 1. And I keep the positives the same. Because really what I'm doing at this point is doing every possible arrangement with 3 positive solutions and our negative. So we'll keep going through every possible choice. And our first one is that we can have 3 positives and 1 negative, which gives us a total of how many solutions? 4. How many are we missing? So the number of complex is 2. Going across any of these rows for this one here should always add up to the degree, which is 6, because our first one, 3 and 3 and 0 does give us 6. 3, 1, and 2 also gives us 6. Okay, we good with this so far? Well, the next thing I would do is subtract 2 from the negatives, but that gives us -1, yes? And for me, anytime I get a negative, I can't keep subtracting from the negatives anymore, I would reset it and see if I can take some from the positives. Well, can we take 2 away from the positives? Yeah, because that would turn this into 1. I reset the negatives back to their highest amount, which is 3. And do it again. Keep taking away from the negatives till I can't anymore. Well, hold on. I got ahead of myself. We still need the complex for this one, yes? 3 and 1 is 4, leaving us with 2. Well, now I start doing the subtraction with the negatives, because I can take 2 away from 3, giving us 1. So we could have 1 positive, 1 negative, and 4 complex to give us a total of 6, yes? Can I take 2 away from the negatives again? No. Can I take 2 away from the positives? No, because that gives us -1 also, yes? So that's it. Those are all the possible combinations of positive, negative, and complex that we can have. So our final answer is this table here. One thing to note is our complex conjugate theorem stated that if A plus BI is a solution, A minus BI is a solution. They come in pairs, which is helpful for us to know because, well, it means the entire complex column should always be even. If they're always coming in pairs, always coming in groups of 2, that column should always be an even set. We're not going to have 1, 3, 5, 7, 9 in the complex set. Because if we have 1, we have to have the other. They always come in pairs of 2. Questions on this here? What do we think of this so far? Not bad. We ready for another one? I'm going to skip this one because, well, it gives us 3 positive, 3 negative. It's the exact same thing. I will tell you this, it is completely possible to get, for a problem like this here, it's not going to be for this one here, but we could have a 4th degree polynomial that has 4 positive zeros, 0 negatives. That's completely possible. Or we can have 0 positives and all negatives. We could have one or the other. Now the nice thing for any of these here, for our positive solutions, positive number of solutions, we can just take the function and start counting our sign changes. And if there is a missing term, we don't have to put it back in. Just count the sign changes. X cubed, x to the fourth to x cubed, positive negative would be 1. X cubed to x squared, negative to positives 2. X squared to our x, it's 3. And our negative to our constant would be 4. So the number of positive solutions we can have is 4. So we can do our subtraction and subtract 2 from it and get 2, because we could also have 2 positive solutions. Can we do it one more time? So the number of possible positive solutions we can have is 4, 2, or 0. Negatives. And again, we're just going through and replacing all the x's with negative x. Now, we're not going to go through the full process we did on the last one, because I did all that to kind of make a point. And the point was that if the power, the exponent's even, the sign stays the same. The sign of the constant stays the same. If the exponent is odd, the sign changes. So if we look at our first term, 3 times negative x to the fourth power is even, so the sign stays the same. Since it was positive, it stays positive. Our next one is x to the third. Third power is odd, so the sign is going to change from negative to positive. So 7x plus 7x cubed. Our next power is x squared. It is even, so the sign stays the same. It'd be plus x squared. Our next one is just first power. First power is odd, so it's going to change from negative 13 to positive 13, and the constant term stays the same because there is no variable to affect it. Questions on this here? Now, yes. Now, honestly, I have a feeling I can see it on some of y'all's faces. Did we really have to write in the parentheses negative x to that power? No. Because if we can see that with which one, the odd power is changing the sign, the even one staying the same, I could have just gone through. Even power stays the same. Odd, flip it. Even stays. Odd, flip. And just gone through and written it with those sign changes as we just pay attention to the powers. But if it isn't, then we need to actually write it out. Okay. Miss Ferris is calling. We'll finish this up here because I think we've got a handle on this, yes? X to the fourth, x to the third goes from positive to positive. So is there a sign change? No. From x to the third to x squared? No. X squared to x? X to our constant? So the number of negatives is 0. That's kind of funny because I said it wouldn't happen on this one, but it did. So now we do our table. Positives, negatives, complex. Always start with the most of each. 4 positives and 0 negatives. And we want 4 because the degree is 4 and we have all 4, yes? Can we subtract 2 from 0? I mean, we can, but we can't have negative 2 solutions. So that means the number of negatives for every case that we're going to have is 0. But I can subtract 2 from the positives, giving us 2, 0. And we're missing 2 because we need a total of 4. Because the number of solutions should equal the degree. And then lastly, we're going to have 0, 0, 4. So going across, positive, negative, complex, each going across, so 4, 0, and 0 should add together to be 4. Our second one, since we had 2 and 0, well, 2 plus 0 is 2. We still needed to equal to 4, so the number of complex would be 2. And since the last one is 0 positive, 0 negatives, 0 solutions, so we have to have 4 complex. Questions on this here? Well, I think we've got a handle on this here. I know we skipped a bunch of the example problems, but I think your guys are good with those there. If you do have additional questions, I believe the videos from last year or the year before do have those. Or if you have questions on it, please ask. I will go over those if you need help.